The Andromeda Galaxy is 2.537 million light-years from Earth. That number appears everywhere in astronomy, usually stated and then forgotten. But stating a number is not the same as understanding it. A light-year is the distance light travels in a year at 299,792 kilometers per second, the fastest speed the universe allows. In a single year, light covers 9.46 trillion kilometers. Multiply that by 2.537 million, and the result becomes so large that it stops feeling like a real distance and starts feeling like an abstraction. What makes Andromeda's distance remarkable is not the number itself, but what lies between us and it. The space between stars contains gas, dust, and scattered matter. The space between galaxies contains almost nothing. It is one of the emptiest environments in the universe, a vast intergalactic void stretching for millions of light years. Reaching Andromeda would mean crossing that void, and the void is worse than you think. The number that does not mean what you think it means. 2.5 million light years. The distance to Andromeda is routinely stated as though it were a fact of the same kind as the distance from London to Tokyo, or even from Earth to the Moon. It is not. The difference is not one of degree, but of category, and understanding that category difference is the first step toward understanding what the distance to the next galaxy actually means. The Moon is 384,400 kilometers from Earth on average. The Apollo 11 mission covered that distance in approximately 3 days using technology developed in the 1960s. The round trip took 8 days. Neil Armstrong and Buzz Aldrin stood on the lunar surface for roughly 2.5 hours. The mission was dangerous, technically demanding, and historically transformative. The distance it covered, in terms of what physics allows, was trivial. Mars, at its closest approach to Earth, sits approximately 54.6 million kilometers away. At its farthest, the separation exceeds 400 million kilometers. A spacecraft traveling at speeds achievable with current propulsion technology takes between 6 and 9 months to make the journey. No human has yet made that trip, but the physics does not prohibit it. The engineering is understood in principle, and several credible mission architectures have been designed in detail. Mars is hard. Mars is not impossible. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. That translates to approximately 40 trillion kilometers. At the speed of the Parker Solar Probe, the fastest spacecraft humanity has ever built, reaching Proxima Centauri would take roughly 6,700 years. No mission to Proxima Centauri has been launched. The engineering required to make such a mission viable within a human lifetime does not yet exist, though proposals involving laser-driven light sails and nuclear propulsion have been developed in theoretical detail. The Andromeda Galaxy is 2.537 million light-years from Earth. It is not 2.537 million times harder to reach than Proxima Centauri. The relationship between distance and difficulty is not linear at these scales. It is not exponential in the sense that engineers discuss exponential difficulty. It approaches a different category entirely, one in which the concepts of reaching, traveling, and arriving begin to lose their meaning in any practical sense. Understanding why requires understanding what light years represent not as a unit of distance, but as a unit of time, and what that means for any object attempting to cross them. Light leaving the Andromeda Galaxy tonight will not reach Earth for 2.537 million years. During that transit time, civilizations on Earth will have risen and fallen. Human beings will have evolved into something unrecognizable or gone extinct. The geography of the continents will have shifted substantially, and the Sun will have aged by 2.537 million years, consuming a measurable fraction of its remaining hydrogen fuel. The light arriving at Earth from Andromeda right now left that galaxy before anatomically modern humans existed. The hominids alive on Earth when that light departed were Homo habilis, using stone tools, walking the savannas of East Africa, with no language, no fire, no concept of the stars above them. That is what 2.537 million light-years means in human terms. And light is the fastest thing that exists. Nothing moves faster. No spacecraft, no signal, no information of any kind can cross the distance to Andromeda faster than light crosses it. The 2.537 million year transit time for a photon is the absolute minimum transit time for anything. A spacecraft moving at 1% the speed of light, which would require propulsion technology far beyond anything currently operational or designed, would take 253.7 million years to reach Andromeda. At 10% of the speed of light, which would require energy expenditures comparable to the total output of the Sun over millions of years, the journey takes 25.37 million years. These are not engineering problems. They are physical constraints imposed by the structure of space-time itself, and they do not yield to ingenuity or funding. What is actually between here and there? The space between the Milky Way and the Andromeda Galaxy is not uniformly empty. It contains structures, objects, and environments that are worth understanding in detail, because the nature of intergalactic space determines what any hypothetical transit through it would encounter, and because those environments are among the most extreme and least understood in the observable universe. The Milky Way and Andromeda are the two dominant members of what astronomers call the local group, a gravitationally bound collection of more than 80 galaxies spread across a volume roughly 10 million light-years in diameter. Most of the local group's members are dwarf galaxies, small irregular or elliptical systems containing anywhere from a few million to a few billion stars, compared to the Milky Way's estimated 200 to 400 billion and Andromeda's estimated 1 trillion. The large and small Magellanic Clouds, visible from the southern hemisphere as distinct patches of light, are dwarf galaxies orbiting the Milky Way at distances of roughly 160,000 and 200,000 light-years respectively. The Triangulum Galaxy, also called M33, is a smaller spiral galaxy roughly 2.7 million light-years away, making it the third largest member of the local group. Scattered between and around these major members are dozens of smaller systems, most discovered only in the past few decades through deep survey imaging. Between these galaxies, connecting and surrounding them, is a medium so diffuse that it makes interstellar space look crowded by comparison. The intergalactic medium consists primarily of ionized hydrogen and helium, the products of Big Bang nucleosynthesis that were never incorporated into stars or galaxies. Its density is extraordinary in its emptiness, approximately 1 particle per cubic meter on average within the local group, compared to the 1 particle per cubic centimeter typical of the interstellar medium within a galaxy. 1 particle per cubic meter. A volume the size of a large room contains a single proton or electron, drifting alone in the dark, separated from the next particle by distances that dwarf the size of the room by orders of magnitude. The intergalactic medium is not cold in the conventional sense. Much of it is heated to temperatures between 100,000 and 10 million Kelvin by the radiation from galaxies and galaxy clusters, and by shock waves produced as gas falls into the gravitational wells of large structures. At these temperatures, the gas is fully ionized, electrons stripped from their nuclei, protons and electrons moving independently at high velocities. Despite these temperatures, the density is so low that the medium contains negligible thermal energy per unit volume. The particles are hot in the sense of moving fast, but there are so few of them that the medium provides essentially no warmth to anything passing through it. A spacecraft in intergalactic space would be surrounded by particles moving at millions of kilometers per hour, while simultaneously experiencing temperatures close to absolute zero from a thermal environment perspective, because so few particles would interact with the spacecraft's surface per unit time. The local group itself is embedded in a larger structure called the Laniakea supercluster, a gravitationally defined region approximately 500 million light-years across, containing more than 100,000 galaxies. Laniakea was formally defined and named only in 2014 when R. Brent Tully at the University of Hawaii and collaborators used galaxy velocity data from the Cosmic Flows catalogue to map the boundaries of the gravitational basin within which the local group resides. The edges of Laniakea are defined not by a physical boundary, but by the watershed between gravitational basins. On one side of the boundary, matter flows toward the centre of Laniakea. On the other side, it flows toward a neighbouring supercluster. The local group sits near the outer edge of Laniakea, flowing inward at several hundred kilometres per second toward the concentration of mass near the centre of the supercluster. Beyond Laniakea, the universe continues with no effective boundary accessible to observation. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. Within that volume, the Andromeda Galaxy is a near neighbour. The Virgo cluster, the nearest large galaxy cluster, sits roughly 53 million light-years away. The Coma cluster, one of the densest known galaxy clusters, is approximately 320 million light-years distant. The most distant confirmed galaxies, detected by the James Webb Space Telescope, are more than 13 billion light-years away. At those distances, the light reaching us today left its source when the universe was less than 400 million years old, less than 3% of its current age. The space between all of these objects shares the same fundamental character as the space between the Milky Way and Andromeda. A near-perfect vacuum, heated to extreme temperatures by diffuse radiation, threaded by the gravitational fields of the structures around it, containing almost nothing. The Andromeda Galaxy at 2.537 million light-years is not far by the standards of the observable universe, but it is unreachably far by any standard that applies to physical objects, including any object humanity could construct or propel. The collision that is already happening. Andromeda is not simply sitting at a fixed distance from the Milky Way, waiting to be observed from afar. It is moving. Everything in the universe is moving, governed by gravity and the expansion of space, and Andromeda's motion relative to the Milky Way is one of the most significant facts about our galactic neighbourhood, because Andromeda is moving toward us. The radial velocity of Andromeda, the component of its motion directly toward or away from Earth, has been measured precisely through Doppler spectroscopy. The shift in the wavelengths of light from Andromeda's stars indicates that the galaxy is approaching at approximately 110 kilometers per second. This measurement has been confirmed repeatedly since it was first made in the early 20th century, when Vesto Slipher at the Lowell Observatory in Arizona measured the blue shift of Andromeda's light in 1912 and found it approaching with a velocity then unprecedented in astronomical observation. Most galaxies beyond the local group show redshift, meaning they are receding as the expansion of the universe carries them away. Andromeda's blue shift was an anomaly that initially puzzled observers before it was understood as the consequence of gravitational attraction overcoming the local expansion of space within the gravitationally bound local group. The transverse velocity of Andromeda, its motion across the sky rather than directly toward Earth, was much harder to measure. The angular motion of an object 2.537 million light-years away is too small to detect directly, even with the most precise astronomical instruments. The measurement was accomplished by Roland van der Marel at the Space Telescope Science Institute and collaborators using the Hubble Space Telescope, measuring the positions of individual stars in Andromeda over years and detecting the tiny shift in position that accumulated over the observation period. Published in 2012, their results indicated a transverse velocity of approximately 17 kilometers per second, much smaller than the radial velocity. This confirmed that Andromeda's trajectory is nearly head-on. The two galaxies are not going to pass by each other, but are on a roughly direct collision course. The collision will not occur on any timescale relevant to human civilization. Current best estimates place the first close approach of the two galaxies at approximately 4.5 billion years from now. The subsequent merger, the full gravitational intertwining and eventual settling into a single combined system, will take several more billion years to complete. The combined galaxy, sometimes called Milkomeda or Milkdromeda in the literature, will likely be an elliptical galaxy, since the merger process tends to disrupt the ordered rotation of spiral galaxies and convert them into the more chaotic structure of ellipticals. What the collision means for individual stars, and for any planets orbiting those stars, is largely nothing. Galaxies are mostly empty space. The average distance between stars in the Milky Way is roughly 4 light-years. When two galaxies collide and interpenetrate, the probability that any individual star physically strikes another star is vanishingly small. The stars are too widely separated for collisions to be common. What changes is the gravitational environment. Stars are flung into new orbits by the tidal forces of the interaction. Some are ejected from the merged system entirely, launched into intergalactic space at hundreds of kilometers per second, condemned to drift through the void forever. The simulations of galaxy mergers, run by teams including T.J. Cox and Avi Loeb at Harvard in the early 2000s, suggest that roughly 12% of stars currently in the Milky Way will be ejected into intergalactic space during the Milkomeda merger. That is, billions of stars, each potentially with planetary systems, sent into permanent exile from any galaxy. The Sun's position during the merger is uncertain. Simulations show a range of possible outcomes, depending on the precise trajectories and timing of the interaction. In some simulations, the solar system is relocated to the outer regions of the merged galaxy. In others, it ends up near the combined center. In approximately 12% of simulated outcomes, it is ejected entirely. The uncertainty reflects genuine physical sensitivity to initial conditions. The merger dynamics are chaotic in the mathematical sense, meaning small differences in the starting parameters produce large differences in outcomes. Understanding that Andromeda is approaching, that a collision is scheduled, and that the merger will be among the most significant events in this galaxy's multi-billion-year history, is not cause for concern on any human timescale. It is worth understanding because it reveals what the distance to Andromeda means in a dynamic sense. The 2.537 million light-years separating us from Andromeda today is not a permanent condition. Gravity is working on it, slowly, relentlessly, across timescales that dwarf human history. The distance is closing. At 110 kilometers per second, it is closing by about 3.5 billion kilometers per year, roughly 23 times the distance from Earth to the Sun. In human terms, that sounds fast. In cosmological terms, at this rate, the full 2.537 million light-year gap would take billions of years to close, which is precisely how long it will take. Why Andromeda looks the way it does from here. On a clear dark night far from city lights, Andromeda is visible to the naked eye as a faint smudge in the constellation of the same name. It is the most distant object visible without optical aid, a dim, elongated glow roughly 6 times the width of the full moon in angular extent, though most of that angular size is too faint for unaided vision. With binoculars, the bright central nucleus becomes distinct, and the disk of the galaxy becomes traceable across several degrees of sky. Through a moderate telescope, dust lanes and the positions of satellite galaxies become visible. The appearance of Andromeda from Earth represents the accumulated light of roughly 1 trillion stars, integrated across 2.537 million light-years of travel, compressed into a faint glow that the human eye can just barely register on the best nights. The light arriving at your eye when you look at Andromeda is 2.537 million years old. The stars producing that light have aged by 2.537 million years since it departed them. Stars have been born and have died in the interval between the emission of that light and your observation of it. The galaxy has rotated slightly. Andromeda rotates with a period of approximately 220 million years at the Sun's equivalent orbital radius, so in 2.537 million years it has rotated by a bit more than 1 degree. The supermassive black hole at Andromeda's centre, designated M31, has accreted additional mass. Andromeda's satellite galaxies have moved in their orbits. Everything about the galaxy you are looking at is 2.537 million years out of date, and there is no way to see it as it is right now because the light showing you its current state has not arrived yet. It will not arrive for 2.537 million years. This temporal displacement is true of everything in the universe beyond the immediate vicinity of Earth. The Moon we see is 1.3 seconds in the past. The Sun is 8.3 minutes in the past. Jupiter is between 33 and 53 minutes in the past, depending on orbital position. The nearest star, Proxima Centauri, is 4.24 years in the past. Andromeda is 2.537 million years in the past. The most distant objects the James Webb Space Telescope has photographed are more than 13 billion years in the past, seen as they existed when the universe was in its infancy. Astronomy is fundamentally an archaeology of light, a reconstruction of the past from the photons that happen to be arriving at our detectors at this particular moment in history. The practical consequence for any hypothetical attempt to reach Andromeda is that navigation would require knowing where Andromeda will be when the spacecraft arrives, not where it appears to be from Earth. For a journey taking millions or tens of millions of years, the target will have moved substantially, rotated considerably, and changed in ways impossible to predict in detail. Andromeda's position 25 million years from now is calculable in broad terms from its current velocity and gravitational environment, but the detailed distribution of mass within the galaxy at that time, including which stars are where and how the spiral arms have wound, is not predictable with any current model. Navigation to a galaxy is a fundamentally different problem from navigation to a star or a planet within a galaxy. The appearance of Andromeda also reveals something important about its nature relative to our own galaxy. Andromeda is a grand spiral galaxy, the largest in the local group by stellar count if not by total mass. Its disk spans roughly 220,000 light-years in diameter compared to the Milky Way's estimated 100,000 light-years. It contains approximately 1 trillion stars, compared to the Milky Way's 200 to 400 billion. It harbours a supermassive black hole at its centre, with a mass of approximately 100 million solar masses, roughly 25 times the mass of the Milky Way's central black hole, Sagittarius A star, which carries about 4 million solar masses. The two galaxies appears in a cosmic sense, comparable in scale, similar in structure, gravitationally dominant within the local group, and heading toward each other at a speed that makes the eventual merger not a question of whether, but only of when. The speed problem, stated honestly, any serious discussion of reaching Andromeda must confront the speed problem directly, without the comfort of vague appeals to future technology or undiscovered physics. The speed problem is this: even if humanity developed propulsion systems capable of accelerating spacecraft to a significant fraction of the speed of light, the time required to cross 2.537 million light-years exceeds the lifespan of any biological organism by many orders of magnitude, and the energy required to propel any macroscopic object to such speeds exceeds the total energy output of the Sun over geological timescales. At 1% of the speed of light, a speed roughly 140 times faster than any spacecraft humanity has built, the journey to Andromeda takes 253.7 million years. The geological record of Earth at 253.7 million years ago shows the Permian-Triassic extinction boundary, the most severe mass extinction in Earth's history, during which approximately 96% of all marine species and 70% of all terrestrial vertebrate species were wiped out. In the 253.7 million years since that event, dinosaurs evolved, flourished for 165 million years, and went extinct. Mammals diversified from small nocturnal survivors into the dominant land vertebrates on the planet. The continents moved by thousands of kilometers. Mountain ranges rose and eroded. Oceans opened and closed. Homo sapiens did not exist for any of that time. The entire history of our species occupies the last 0.12% of that interval. At 10% of the speed of light, requiring energy inputs that no human engineering project could approach with any plausible technology, the journey takes 25.37 million years. That interval spans from the early Miocene epoch to the present. It encompasses the evolution of the great apes, the emergence of the hominid lineage, and the full cognitive and physical development of humans from a common ancestor with chimpanzees. No civilization, no institution, no record-keeping system of any kind has persisted for a fraction of that duration. At 50% of the speed of light, where relativistic effects become significant and the energy required reaches values that dwarf any conceivable power source, the journey takes approximately 5 million years. Time dilation at this speed would reduce the experienced travel time for passengers on the spacecraft to something less than 5 million years. But the reduction is not dramatic. At 50% of the speed of light, the Lorentz factor is approximately 1.15, meaning passengers experience about 4.35 million years of travel. Still incomprehensible. Still utterly beyond the scope of any biological lifespan. At 99% of the speed of light, approaching the physical limit, the Lorentz factor is approximately 7.09. The experienced travel time for passengers would be roughly 358,000 years. At 99.9% of the speed of light, the Lorentz factor is approximately 22.4, and the experienced travel time drops to roughly 113,000 years. At 99.9999% of the speed of light, the Lorentz factor reaches approximately 707, and experienced travel time falls to roughly 3,600 years. Still longer than recorded human civilization. Still utterly beyond the reach of any biological organism. The energy required to accelerate a spacecraft to these velocities scales with the Lorentz factor. At 99.9999% of the speed of light, accelerating a 1 kilogram mass requires kinetic energy of roughly 707 times its rest mass energy, which is 707 times 90 petajoules, approximately 63,630 petajoules per kilogram of spacecraft mass. For a spacecraft massing 10 metric tons, which is lighter than a small car and far too light for any inhabited vessel, the energy requirement is approximately 636 exajoules. The total annual energy consumption of human civilization is roughly 580 exajoules. Accelerating a 10 metric ton spacecraft to 99.9999% of the speed of light would require more than the entire global energy production of the human species for a full year. Devoted entirely to this single purpose, achieving nothing in terms of inhabited space or scientific capability. And the spacecraft would still take 3,600 years by its own clock to reach its destination. These numbers are not presented to argue that interstellar or intergalactic travel is categorically impossible under all conceivable future physics. They are presented because they define the scale of the problem accurately, and that scale is routinely underrepresented in discussions of space exploration that treat the distance to other galaxies as an engineering challenge, rather than a physical constraint of a fundamentally different character from any challenge human civilization has previously faced. The local group as prison and home. The local group of galaxies, the gravitationally bound cluster of more than 80 galaxies, of which the Milky Way and Andromeda are the dominant members, has a specific physical character that is worth understanding in detail. It is the only region of the universe that is, in principle, accessible to physical travel from Earth on timescales shorter than the age of the universe, and even that accessibility is conditional on physical capabilities far beyond anything currently achievable. The local group spans roughly 10 million light-years in its longest dimension. Its total mass is dominated by dark matter, the invisible gravitating substance that outweighs visible baryonic matter by approximately 5 to 1 in the universe as a whole. The local group's total mass has been estimated at approximately 4 to 5 trillion solar masses, of which perhaps 3 trillion solar masses is dark matter distributed in halos around the member galaxies and filling the volume between them. The visible matter, stars, gas and dust, accounts for the remaining 1 to 2 trillion solar masses concentrated in the member galaxies. The gravitational binding of the local group means that its member galaxies are not participating in the general expansion of the universe in the way that more distant galaxies are. The expansion of the universe, the systematic recession of distant galaxies described by the Hubble-Lemaitre law, is a property of the fabric of space-time on large scales. On small scales, within gravitationally bound structures, the expansion is overcome by gravity and does not cause objects to recede from each other. The Moon is not getting farther from Earth due to cosmic expansion. The Earth is not getting farther from the Sun. The Sun is not drifting away from the rest of the Milky Way. Andromeda is not drifting away from the Milky Way. All of these objects are gravitationally bound in systems whose internal gravity exceeds the expansive effect of dark energy on the relevant scales. The edge of the local group, the boundary beyond which the expansion of the universe carries objects away faster than gravity can draw them back, sits at roughly 5 million light-years from the local group's centre of mass. Beyond that boundary, the member galaxies of neighbouring galaxy groups are receding and will continue to recede indefinitely. The Virgo cluster, the nearest large concentration of galaxies outside the local group at roughly 53 million light-years away, is moving away from us at approximately 1,100 kilometres per second due to the Hubble expansion. Reaching it would require covering 53 million light-years of intergalactic space against a headwind of expanding space-time that is continuously increasing the distance to be covered. This is the cosmological horizon problem applied to intergalactic travel. For objects beyond the local group, the expansion of space is working actively against any attempt to cross the intervening distance. A spacecraft launched from Earth toward the Virgo cluster today, travelling at 1% of the speed of light, would find the Virgo cluster receding faster than the spacecraft approaches. The spacecraft would never arrive. The expansion would continuously add distance faster than the spacecraft covered it. To reach the Virgo cluster by direct travel would require a spacecraft capable of velocities significantly in excess of the current recession speed of the cluster, which grows over time as the universe expands. In an accelerating universe driven by dark energy, objects beyond a certain distance are already receding faster than light, meaning no signal and no spacecraft can ever reach them regardless of speed. The local group is, in this precise sense, the maximum extent of any physical influence that Earth-based civilization can exert on the universe. The galaxies within it are gravitationally bound to our own and will not recede beyond reach as the universe expands. The galaxies beyond it are already effectively gone. They are moving away from us and will continue to do so, with the separating velocity growing over time as dark energy accelerates the expansion. The observable universe contains roughly 2 trillion galaxies. The local group contains more than 80. Everything else in the observable universe is, on cosmological timescales, becoming permanently and irreversibly separated from us by the expansion of space. The local group is not merely our neighbourhood, it is our entire accessible universe, and even within it, the distances are measured in millions of light-years. What astronomers actually know about Andromeda. Everything known about the Andromeda Galaxy has been learned from Earth, using photons that travelled 2.537 million light-years to reach our instruments. No probe has visited Andromeda, no signal has been sent there and returned. No physical sample of Andromeda has ever been available for analysis. The knowledge accumulated about this galaxy over more than a century of systematic observation is therefore a remarkable demonstration of what can be extracted from light alone. and also a reminder of what light cannot tell us. The systematic study of Andromeda began in earnest in the early 20th century, when it was still classified as a nebula, a term applied to any diffuse celestial object. In 1912, Henrietta Swan Leavitt at the Harvard College Observatory published her discovery that Cepheid variable stars, stars that pulsate in brightness with a regular period, have a period that is directly related to their intrinsic luminosity. By measuring the period of a Cepheid and looking up the corresponding luminosity on Leavitt's calibrated period-luminosity relationship, an astronomer could calculate the star's true brightness and then compare that true brightness to its observed apparent brightness to derive its distance. The dimmer a star of known brightness appears, the farther away it must be. Edwin Hubble applied Leavitt's Cepheid method to variable stars he identified in the Andromeda Nebula using the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the largest operational telescope in the world. In a series of observations in 1923 and 1924, Hubble identified and measured the periods of Cepheid variables in Andromeda and calculated their distances. His results, communicated to the American Astronomical Society in January 1925, demonstrated that the Andromeda Nebula was not a cloud of gas within the Milky Way, but an entirely separate system of stars roughly 900,000 light-years away. The actual distance, corrected by subsequent improvements in the Cepheid calibration, is 2.537 million light-years, but Hubble's measurement was sufficient to establish that Andromeda lay far outside the Milky Way, that it was a galaxy in its own right, and that the universe was vastly larger than any previous estimate had suggested. Modern knowledge of Andromeda's structure has been built through observations across the full electromagnetic spectrum, from radio wavelengths through infrared, optical, ultraviolet, X-ray, and gamma ray. Radio observations have mapped the distribution of neutral hydrogen gas throughout the galaxy, revealing its spiral arm structure extending far beyond what optical images show. Infrared observations have penetrated the dust lanes that obscure large portions of the galaxy at optical wavelengths, revealing star formation activity in otherwise invisible regions. X-ray observations have identified dozens of X-ray binary systems within the galaxy, pairs of stars in which one member is a neutron star or black hole accreting material from its companion and producing powerful X-ray emission. Ultraviolet observations have mapped the distribution of hot young stars, tracing the locations of recent star formation. Andromeda's stellar population contains stars at every stage of evolution. Massive blue stars, tens of times the mass of the Sun, burning hydrogen rapidly and destined to explode as supernovae within millions of years. Sun-like yellow stars fusing hydrogen in their cores on timescales of billions of years. Old red giant stars in the late stages of their lives, having exhausted their core hydrogen and expanded to enormous sizes. White dwarfs, the cooling remnants of stars like the Sun, after they have shed their outer layers and left their dense cores exposed. Neutron stars and black holes, the remnants of massive stars that have ended their lives in supernova explosions. The full history of stellar evolution is represented in Andromeda's stellar population, written in the light that reaches our telescopes. The central region of Andromeda has been studied in particular detail because it contains one of the most unusual galactic centers known. Hubble Space Telescope images revealed that Andromeda's nucleus appears double, two distinct concentrations of stars displaced from each other by roughly 5 light-years. This double nucleus was explained by Scott Tremaine at Princeton in 1995 as an optical illusion produced by the eccentric disk of stars orbiting the central supermassive black hole. Stars on eccentric orbits spend more time near their farthest point from the black hole than near their closest point, producing an apparent concentration of stars offset from the center. The actual center, where the supermassive black hole resides, is marked by a compact cluster of blue stars orbiting the black hole at distances of only a few light-years. The satellites of Andromeda and what they reveal. Andromeda is not alone. Like the Milky Way, it is surrounded by a retinue of satellite galaxies, smaller gravitationally bound systems orbiting the larger spiral at distances ranging from tens of thousands to several 100,000 light-years from Andromeda's center. The population of Andromeda's satellites is extensive, and its study has revealed patterns of galaxy formation and evolution that challenge aspects of the standard theoretical framework. The two largest and most prominent satellite galaxies of Andromeda are M32 and M110, both visible through moderate telescopes on dark nights as compact companions to the main galaxy disk. M32 is a compact elliptical galaxy, roughly 6,500 light-years in diameter, containing approximately 3 billion stars packed into a region far smaller than most galaxies of comparable stellar mass. Its compactness is thought to result from tidal stripping. Interactions with Andromeda's gravitational field have removed the outer layers of what was once a larger galaxy, leaving only the dense central core. M110 is a larger elliptical dwarf containing several billion stars, extended over a region roughly 17,000 light-years across, with a more diffuse structure than M32. Beyond these two prominent satellites, Andromeda's halo contains a large population of dwarf galaxies, most discovered through systematic photometric surveys in the early 21st century. The Pan-Andromeda Archaeological Survey, known as PAN-DARS, used the Canada-France-Hawaii telescope to map the halo of Andromeda over thousands of square degrees of sky in unprecedented depth, revealing streams of stars torn from satellite galaxies by tidal forces, overdensities corresponding to newly discovered dwarf galaxies, and the complex substructure of a galaxy that has been accreting smaller companions throughout its history. One feature of Andromeda's satellite population has attracted sustained attention and generated significant theoretical debate. A large fraction of Andromeda's satellite galaxies are arranged in a thin plane, rather than being distributed isotropically around the parent galaxy. This planar arrangement, identified in detail by Rodrigo Ibata at the Strasbourg Astronomical Observatory and collaborators in a 2013 paper in Nature, involves approximately 15 satellite galaxies distributed in a disk-like structure roughly 1 million light-years in diameter, but only 50,000 light-years thick. The satellites in this plane appear to be co-rotating, orbiting Andromeda in the same direction around the same axis, rather than moving in random orbits. The theoretical problem is that the standard model of galaxy formation, the lambda cold dark matter framework, predicts that satellite galaxies should be distributed approximately isotropically around their parent galaxies, reflecting the roughly spherical distribution of dark matter halos in which they formed. Thin planar arrangements of co-rotating satellites are rare in lambda cold dark matter simulations. The Milky Way has a similar structure. Its satellite galaxies, including the Magellanic Clouds, are preferentially distributed in a vast polar plane known as the vast polar structure. The presence of analogous planar arrangements in both the Milky Way and Andromeda, studied independently with different methods, has been interpreted by some researchers as evidence of a systematic failure of the standard model on small scales, and by others as a selection effect, or the result of coherent accretion of satellites along cosmic filaments. The debate remains active in the literature. The stellar streams surrounding Andromeda, visible in the PAN-DARS survey data as ghostly arcs and ribbons of stars extending across hundreds of thousands of light-years, are the archaeological record of past mergers. Each stream is the disrupted remnant of a smaller galaxy that fell into Andromeda's gravitational field, was torn apart by tidal forces, and stretched along its orbital path into a ribbon of stars. The giant stellar stream, the most prominent such feature, extends roughly 500,000 light-years from Andromeda's center and is estimated to contain tens of millions of stars. By analysing the chemistry and kinematics of the stars in these streams, astronomers can reconstruct the properties of the galaxies that were destroyed and the timeline of their accretion, reading Andromeda's merger history in the same way that geologists read Earth's history in rock strata. What reaching Andromeda would actually require. Taking the distance seriously as a physical problem rather than a rhetorical one requires specifying as concretely as possible what a mission to Andromeda would demand in terms of energy, time, and technology. The exercise is not intended to make the case that such a mission is achievable. It is intended to establish the actual scale of the requirement, which differs qualitatively from any challenge human civilization has previously confronted. The most favourable scenario for minimising travel time invokes relativistic time dilation. As a spacecraft approaches the speed of light, the experience time aboard the spacecraft is reduced relative to time elapsed at the departure point. At 99.99999% of the speed of light, the Lorentz factor is approximately 2,236. And a journey of 2.537 million light-years takes roughly 1,135 years of experience time aboard the spacecraft. This is the most optimistic conceivable scenario, requiring a speed so close to light that no realistic physical mechanism has been identified that could achieve it for a macroscopic object. But even in this scenario, the passengers experience more than 1,000 years of travel. No human civilization has maintained institutional continuity, technological sophistication, and mission focus for 1,000 years. The Roman Empire at its height lasted roughly 5 centuries before fragmenting. The Catholic Church is among the oldest continuous institutions in recorded history and has existed for roughly 2,000 years, though not without profound transformations. A 1,000-year mission would need to sustain itself through changes in technology, culture, governance, and purpose that make any current prediction about the crew's state of knowledge or motivation at arrival purely speculative. The energy required to accelerate a spacecraft to 99.99999% of the speed of light is calculated from relativistic mechanics. The total energy, kinetic plus rest mass, of an object at this speed is its rest mass energy multiplied by the Lorentz factor of 2,236. For a spacecraft with a dry mass of 1,000 metric tons, which is comparable to the International Space Station and far too small for a 1,000-year inhabited mission, the kinetic energy at this speed is approximately 2,236 times the rest mass energy of 1,000 metric tons. The rest mass energy of 1,000 metric tons is about 9 times 10 to the 22nd joules. The kinetic energy at 99.99999% of light speed is therefore roughly 2 times 10 to the 26th joules. The Sun's total luminosity, the total energy it radiates per second, is approximately 3.8 times 10 to the 26th joules. Accelerating this hypothetical spacecraft to this speed would require an energy expenditure roughly comparable to the Sun's total output for a fraction of a second, but concentrated and directed with perfect efficiency into propulsion. No conceivable propulsion mechanism converts energy to momentum with anything approaching this efficiency. A perfect photon rocket, the theoretically optimal propulsion system in which all energy is converted to photons directed opposite the direction of travel, achieves a mass ratio, the ratio of initial fueled mass to final payload mass, that scales as the square of the Lorentz factor. For a Lorentz factor of 2,236, the mass ratio is approximately 5 million. For every kilogram of payload delivered to the destination, 5 million kilograms of fuel must be consumed at departure. For a 1,000 metric ton spacecraft, approximately 5 billion metric tons of fuel would be required, and this fuel must itself be accelerated during the early part of the journey, requiring additional fuel to accelerate the fuel in the compounding fashion described by the rocket equation. The actual fuel requirement in a realistic scenario, accounting for the rocket equation's compounding effect, exceeds any mass that human civilization could conceivably assemble or process. These are not objections to cleverness or ambition. They are the output of the most fundamental equations of physics applied to the actual numbers involved. The energy and mass requirements for a relativistic crossing of even the nearest intergalactic distance are not large in the way that, say, building a particle accelerator is large. They are large in the way that rearranging a significant fraction of the mass energy of the solar system is large. They belong to a different category of challenge entirely. Why we can learn everything and go nowhere. The profound asymmetry of the Andromeda situation is this: we can learn an enormous amount about the galaxy without going there, and no amount of learning brings us any closer to the physical capacity to cross the distance. The Andromeda Galaxy is, in a specific sense, the most studied unreachable object in the universe. It is close enough to resolve individual stars, to map its spiral structure, to measure the orbits of its satellite galaxies, to detect individual X-ray binary systems within it. It is far enough away that the light reaching us today is 2.537 million years old that no physical object launched from Earth today will arrive within any cosmologically relevant time frame, and that any signal sent toward it will not arrive for 2.537 million years. The Hubble Space Telescope has resolved individual stars in Andromeda. The Wide Field Camera 3 aboard Hubble, in a program called the Panchromatic Hubble Andromeda Treasury, mapped more than 100 million individual stars in Andromeda's disk, producing the most detailed portrait of another galaxy ever assembled. The survey covered a region stretching from the compact star-forming regions in the galaxy's inner disk to the sparse stellar halo at its edges, capturing stars at every stage of evolution, from young, massive blue stars to ancient red giants. Each star in that survey is a sun in its own right, potentially orbited by its own family of planets, potentially harboring its own forms of chemistry and perhaps biology. And every one of those stars is 2.537 million light-years away. The James Webb Space Telescope, operating from 2022 onward, has extended this kind of detailed stellar archaeology to Andromeda and to more distant members of the local group with unprecedented infrared sensitivity. Its ability to detect cool, low-luminosity stars that were invisible to Hubble has expanded the census of Andromeda's stellar population and refined measurements of its star formation history. The infrared wavelengths to which Webb is sensitive penetrate the dust that obscures large regions of Andromeda at optical wavelengths, revealing star formation activity in previously hidden regions of the disk. Radio telescopes, particularly the Very Large Array in New Mexico and the Westerbork Synthesis Radio Telescope in the Netherlands, have mapped the distribution of neutral atomic hydrogen across Andromeda's disk and halo through observations of the 21-centimetre emission line, the characteristic radio wavelength emitted when neutral hydrogen atoms flip their electron spin. These observations reveal the galaxy's gaseous skeleton, the reservoir of material from which future stars will form, extending even farther than the stellar disk visible in optical images. The neutral hydrogen distribution shows the disturbed morphology produced by gravitational interaction with satellite galaxies and the faint signatures of streams connecting Andromeda to its satellites. All of this knowledge, accumulated through decades of observation across the electromagnetic spectrum, has been gathered without leaving Earth. The photons were free to travel. The information they carried about the structure, composition, kinematics and history of the Andromeda Galaxy arrived at the speed of light, the fastest information can travel, and was decoded by instruments sensitive enough to extract it from the faint signals. This is humanity's relationship with Andromeda. We can observe it in extraordinary detail. We can reconstruct its past history across billions of years. We can model its future trajectory over the next 5 billion years, and we are completely unable to send anything there, receive anything from there, or affect anything there in any way that would be detectable within any human timescale. The distance does not prevent knowledge, it prevents contact. It prevents influence. It prevents the kind of relationship with Andromeda that involves physical presence, sample return, direct measurement, or any form of interaction that requires something to travel between the two galaxies rather than merely light to carry information in one direction. We know Andromeda intimately in the way that a person might know the biography of someone who died millions of years before they were born, in complete detail from the historical record, and with absolute impossibility of any personal encounter. The expansion of space and why it is not what you think. The universe is expanding. That statement has been in scientific circulation since Edwin Hubble published his observations of galaxy recession velocities in 1929, and it has been repeated so often in popular science that it has acquired the comfortable texture of a familiar fact. What it means, physically and geometrically, is almost universally misunderstood, and the misunderstanding matters enormously for any attempt to reason about the distance to Andromeda and to galaxies beyond the local group. The expansion of the universe is not the motion of galaxies through space. It is the expansion of space itself, the fabric in which galaxies are embedded. The distinction is not semantic. When a galaxy recedes from us due to the Hubble expansion, it is not moving through a pre-existing empty stage, accelerating away from a center like debris from an explosion. Space itself is growing, and the galaxies are being carried along by that growth the way raisins in a rising loaf of bread are carried apart as the dough expands. No raisin is moving through the dough. The dough is growing, and the distance between every pair of raisins is increasing as a result. The practical consequence of this distinction is that recession velocities due to the expansion of space are not constrained by the speed of light in the same way that motions through space are constrained. Special relativity prohibits objects from moving through space faster than light. It does not prohibit space itself from expanding at any rate. Galaxies sufficiently far from Earth are already receding faster than the speed of light, not because they are moving through space at superluminal speeds, but because the space between them and Earth is expanding fast enough that the total distance is increasing at a rate exceeding the speed of light. Light emitted by those galaxies today is moving toward Earth at the speed of light through local space, but the space through which it is moving is expanding at a rate that exceeds the light's progress. That light will never reach Earth. Those galaxies are already, permanently, beyond our reach and beyond our observational horizon in the future. The distance at which this occurs, the distance at which galaxies are currently receding from Earth at exactly the speed of light, defines the Hubble sphere. Its radius is approximately 14.4 billion light-years, corresponding to a recession velocity equal to the speed of light at the current value of the Hubble constant, approximately 67 to 73 kilometers per second per megaparsec, depending on which measurement method is used. Galaxies inside the Hubble sphere are receding at less than the speed of light, and light they emit can in principle reach Earth if it is moving in our direction. Galaxies outside the Hubble sphere are receding faster than light, but light they emitted in the past, when they were closer and moving more slowly, is still travelling toward us and can still reach us. The observable universe therefore extends beyond the Hubble sphere to a distance of approximately 46.5 billion light-years, because we are seeing those distant galaxies as they were in the past, when they were within the Hubble sphere. Andromeda, at 2.537 million light-years, is well inside the Hubble sphere and is in fact gravitationally bound to the Milky Way, so it is not receding at all despite the expansion. The galaxies of the Virgo cluster, at roughly 53 million light-years, are receding at approximately 1,100 kilometers per second, well below the speed of light, but still receding. Each year, the distance to the Virgo cluster increases by approximately 35 billion kilometers due to the expansion alone, before any gravitational corrections are applied. A spacecraft launched from Earth toward the Virgo cluster at 1% of the speed of light would be moving at approximately 3,000 kilometers per second toward it, while the cluster recedes at 1,100 kilometers per second. The spacecraft would approach at a net rate of roughly 1,900 kilometers per second, taking approximately 850,000 years to arrive. In that 850,000 years, the expansion of space would have moved the cluster considerably farther than its current 53 million light-years, requiring continuous recalculation of the trajectory. The spacecraft would arrive eventually, if it survived long enough and maintained its velocity throughout. But 1% of the speed of light is roughly 140 times faster than any spacecraft humanity has built, and 850,000 years is roughly 10 times the duration of the entire Pleistocene epoch that shaped human evolution. For galaxies at cosmological distances beyond a few hundred million light-years, the recession velocity approaches and then exceeds the speed of light. Any spacecraft launched from Earth today toward a galaxy receding faster than light would never reach it. The expansion of space would continuously work against the spacecraft's motion, adding distance faster than the spacecraft could cover it, even at velocities approaching the speed of light. This is not a consequence of any limitation in propulsion technology. It is a consequence of the geometry of an accelerating, expanding universe, and it defines the absolute boundary of what is physically accessible from Earth. The Andromeda Galaxy is on the correct side of this boundary. It is gravitationally bound to us and is not receding, but it is still 2.537 million light-years away, and the speed problem analysed in Chapter 5 applies in full regardless of expansion. The expansion merely adds an additional layer of inaccessibility on top of the distance problem for all galaxies beyond the local group. The mathematics of expansion and accessibility were worked out in detail by Charles Lineweaver and Tamara Davis at the University of New South Wales in a 2005 paper in Scientific American that clarified several persistent misconceptions about cosmic expansion. Their key insight was the distinction between the observable universe, defined by the look-back time horizon, and the reachable universe, defined by the cosmic event horizon. The observable universe contains all objects from which light has had time to reach us since the Big Bang, a sphere approximately 46.5 billion light-years in radius. The reachable universe contains all objects that a spacecraft or signal launched from Earth today could eventually reach, given infinite time, accounting for the accelerating expansion. These two spheres are not the same. The reachable universe is smaller than the observable universe. Objects near the edge of the observable universe, currently at distances of tens of billions of light-years, are receding so fast that nothing launched from Earth today could ever catch them. The expansion of space between us and them adds distance faster than any spacecraft or signal could cover it. The boundary of the reachable universe, the cosmic event horizon, is currently at approximately 16 billion light-years. Objects beyond this boundary are, in a physically precise sense, permanently inaccessible. They are moving away from us faster than light, and any signal launched toward them today will never arrive. This boundary is not fixed. As dark energy continues to accelerate the expansion, the event horizon may shrink or expand, depending on the equation of state of dark energy, which remains uncertain. The local group sits entirely within the reachable universe, being gravitationally bound and not participating in the Hubble flow. This is the specific sense in which the local group is humanity's accessible universe. Everything within it is in principle reachable, however difficult the journey, and everything beyond it is either barely reachable within extreme timescales or permanently beyond reach. Andromeda, at 2.537 million light-years, is well within this boundary. The nearest galaxy groups beyond the local group, at 10 to 15 million light-years, are also within the event horizon and are technically reachable, though the journey would require millions of years even at relativistic speeds, and the expansion is continuously increasing the distance to be covered. The Virgo cluster, at 53 million light-years, is within the event horizon as well, though just barely accessible in this sense. Beyond a few hundred million light-years, the practical reachability becomes so marginal that the distinction between technically accessible and permanently inaccessible loses operational meaning. Dark energy and the accelerating separation. The expansion of the universe is not merely continuing at a steady rate, it is accelerating. The discovery of this acceleration, announced in 1998 by two independent teams, the Supernova Cosmology Project led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University, was one of the most surprising results in the history of cosmology. Perlmutter, Schmidt and Rees received the Nobel Prize in Physics in 2011 for this work. The evidence came from measurements of Type Ia supernovae, thermonuclear explosions of white dwarf stars that occur when they accrete enough mass from a companion to exceed the Chandrasekhar limit of approximately 1.4 solar masses. Type Ia supernovae have a characteristic intrinsic brightness that can be calibrated from the shape of their light curves, making them standard candles for measuring cosmic distances, in the same way that Leavitt's Cepheid period luminosity relationship provides a standard candle at shorter distances. By measuring the observed brightness and redshift of Type Ia supernovae at cosmological distances, the two teams could determine whether the expansion of the universe was decelerating, as expected, from a matter-dominated universe where gravity should slow the expansion, or accelerating. They found acceleration. Distant supernovae were dimmer than expected, meaning they were farther away than a decelerating expansion would have placed them. The expansion had been speeding up. The agent responsible for this acceleration is called dark energy, a name assigned to whatever physical mechanism is causing space to expand faster over time. Dark energy comprises approximately 68% of the total energy content of the universe. Its nature is unknown. It may be the cosmological constant that Einstein introduced into his field equations in 1917 and later called his greatest blunder, a constant energy density inherent to the vacuum of space that does not dilute as the universe expands. It may be a dynamical field called quintessence that varies across space and time. The Dark Energy Spectroscopic Instrument released results in 2024 suggesting that dark energy may be evolving over cosmic time, potentially changing in strength, which would distinguish it from a true cosmological constant. Whether that result holds under further scrutiny will determine which theoretical description of dark energy is viable. What dark energy means for the accessibility of other galaxies is specific and disquieting. In an accelerating universe, the cosmic event horizon, the boundary beyond which objects are receding faster than light, is not fixed. As the expansion accelerates, the event horizon shrinks in comoving coordinates, meaning that objects that are currently within our reach in principle, in the sense that light they emit now can eventually reach us, are progressively losing that status. Over the next tens of billions of years, as dark energy continues to accelerate the expansion, galaxies that are currently observable will cease to be so. Their recession velocities will exceed the speed of light, and they will disappear from the observable universe forever. The total number of galaxies that will ever be observable from Earth, considering not just those visible now, but those whose light will eventually reach us, is finite and calculating. It was attempted by Abraham Loeb at Harvard and collaborators. Their analysis suggests that approximately 20% of all galaxies currently within the observable universe will eventually become visible as their light continues to travel toward us. The remaining 80% are already receding so fast that even light they emitted long ago will never reach us. And over the coming trillions of years, even the 20% that are currently reachable in principle will progressively cross the event horizon as the acceleration continues, leaving eventually only the gravitationally bound local group visible in the night sky. For the practical question of reaching Andromeda, dark energy does not change the fundamental analysis. Andromeda is gravitationally bound to us and will not be separated by the expansion. But dark energy's existence confirms that the universe beyond the local group is, on cosmological timescales, actively and irreversibly becoming less accessible rather than more. Every year, more galaxies cross the event horizon and are permanently removed from the set of objects that could, in principle, be influenced by anything originating on Earth. The universe is not waiting patiently to be explored. It is, in a fundamental physical sense, shrinking the domain of what is accessible, relentlessly and permanently. The energy density of dark energy is estimated at approximately 6.9 times 10 to the minus 27 kilograms per cubic meter, or in energy terms, roughly 6 times 10 to the minus 10 joules per cubic meter. This is an extraordinarily small energy density by any everyday standard. A typical incandescent light bulb radiates about 60 joules per second into a room of perhaps 30 cubic meters, giving an average energy density in the room that is roughly 10 to the 25th times denser than the dark energy of the universe. Yet despite this near negligible energy density, dark energy dominates the total energy content of the universe because it is present everywhere, filling all of the enormous volume of empty space that constitutes most of the universe, with an energy density that does not decrease as the universe expands. Dark energy's total contribution grows as the universe grows, because there is more space, and each cubic meter of that space carries the same dark energy density. Matter, by contrast, dilutes as the universe expands. The same amount of mass spread over a larger volume gives a lower mass density. This is why dark energy, negligible in comparison to matter in the early dense universe, now dominates the energy budget and drives the accelerating expansion. Matter's contribution has diluted with expansion, while dark energy's contribution has grown with the increasing volume. The Dark Energy Spectroscopic Instruments 2024 results, suggesting that dark energy may be dynamical rather than a true cosmological constant, add a layer of uncertainty to the long-term future of the universe's expansion. If dark energy is weakening over time, the expansion may eventually decelerate, halt, and reverse, leading to a big crunch scenario, in which the universe collapses back to a singularity on timescales of tens of billions of years. If dark energy is strengthening, the expansion could accelerate to the point where the repulsive force overcomes the electromagnetic and nuclear forces binding matter together, leading to a big rip in which every structure in the universe, from galaxy clusters to atoms, is torn apart in sequence as the expansion rate increases without limit. The current data do not definitively determine which of these futures awaits, but they have established that the cosmological constant is not the complete picture, and that the ultimate fate of the universe remains an open question. The intergalactic void and what crossing it would mean. The space between the Milky Way and Andromeda is not the space between two nearby objects separated by a lot of nothing. It is the intergalactic void, a physical environment so different from anything in human experience that describing it in familiar terms requires constant qualification. Understanding what that void actually is, physically, matters for understanding what crossing it would mean. Within the Milky Way, the interstellar medium is sparse but present. Gas clouds of molecular hydrogen, the birthplaces of stars, contain between 100 and 1 million molecules per cubic centimetre. The warm neutral medium that fills most of the galactic disk contains approximately 1 atom per cubic centimetre. Even the hot, rarefied gas filling the space between the spiral arms at temperatures of millions of Kelvin contains roughly 10 to the minus 3 particles per cubic centimetre, 1,000 times less dense than the warm neutral medium, but still far denser than the intergalactic medium. The intergalactic medium within the local group contains approximately 1 particle per cubic metre, roughly 10 to the minus 6 particles per cubic centimetre. This is 6 orders of magnitude emptier than the hot gas within the Milky Way. And the hot gas within the Milky Way is already among the least dense environments in human experience. Laboratory vacuum chambers on Earth achieve pressures corresponding to roughly 10 to the 11 particles per cubic centimetre. The intergalactic medium is 10 to the 17 times emptier than the best laboratory vacuum. There is essentially nothing between the Milky Way and Andromeda. Yet this near-nothingness has physical structure. The intergalactic medium within the local group is threaded by the gravitational fields of the Milky Way and Andromeda, which create a potential well in which the member galaxies orbit and through which material flows. It contains the stellar streams produced by tidally disrupted satellite galaxies, thin ribbons of stars extending across hundreds of thousands of light years. It carries the magnetic fields that permeate the galactic halos, weak but measurable fields with strengths of order 1 nanogauss, generated by dynamo processes within the galaxies and extended into the surrounding medium by galactic winds and jets. It is ionized by the ultraviolet radiation from stars and quasars throughout the local group and beyond, keeping the hydrogen that fills this medium in a plasma state rather than a neutral atomic state. A spacecraft traveling through this medium at a significant fraction of the speed of light would experience the intergalactic medium as a flux of particles striking the spacecraft's leading face. At 10% of the speed of light, the effective particle density in the spacecraft's reference frame is increased by the Lorentz contraction of the space in the direction of motion, and the kinetic energy of each particle-spacecraft collision is correspondingly increased. Even at 1 particle per cubic metre in the rest frame, the flux of particles striking a 1 square metre surface at 10% of the speed of light is approximately 3 times 10 to the 7 particles per second, each carrying kinetic energy of roughly 1.5 times 10 to the minus 16 joules in the spacecraft's frame. The total power deposited by these collisions is approximately 4.5 times 10 to the minus 9 watts per square metre, negligible for a spacecraft's power budget, but not negligible for radiation damage over millions of years of travel. The more serious concern is cosmic ray bombardment. Cosmic rays, high-energy charged particles accelerated to relativistic speeds by supernova remnants, pulsars, active galactic nuclei, and other energetic astrophysical sources, permeate intergalactic space at lower densities than within galaxies, but still present a significant radiation hazard over long exposure times. The cosmic ray flux in intergalactic space is not well measured directly, because our measurements are dominated by the local galactic cosmic ray population, but modelling suggests it is reduced by 1 to 2 orders of magnitude compared to the interstellar cosmic ray flux within the Milky Way. For a mission lasting millions of years, even this reduced flux accumulates into a total radiation dose that would be lethal to biological tissue without substantial shielding, and would cause cumulative damage to electronic components sufficient to require redundant replacement on timescales far shorter than the journey duration. The psychological environment of intergalactic travel is worth contemplating separately from the physical environment, not because it changes the physical analysis, but because it reveals something about the category difference between intergalactic travel and any form of travel humans have previously undertaken. Within the solar system, the sky contains the Sun, the planets, and thousands of stars. Within the Milky Way, the sky contains the band of the galaxy, the nearest galaxies visible to the naked eye, and 2 trillion stars resolved into a bright background by the galaxy's disk. In intergalactic space, between the Milky Way and Andromeda, the sky contains the 2 galaxies receding and approaching as fuzzy glows, the scattered dwarf members of the local group as faint smudges, and the distant universe as a field of more distant galaxy clusters. The stars familiar from Earth's sky are gone. The constellations are gone. The Sun is a faint, unremarkable point of light, indistinguishable from billions of other stars in the receding smear of the Milky Way. Nothing in the evolutionary history of any biological organism has prepared any nervous system for this visual environment, and no amount of prior knowledge makes it emotionally tractable in the way that abstract knowledge of a thing differs from being inside it. The navigational challenges of intergalactic travel deserve specific attention, because they differ qualitatively from interplanetary or interstellar navigation. Within the solar system, navigation uses the Sun as a fixed reference point. Planetary ephemerides calculated from precise orbital mechanics and the ability to send correction signals to spacecraft from Earth with a round-trip communication time of minutes to hours. Errors are caught and corrected in near real time. Within the galaxy, stars serve as navigational reference points, and communication delays are measured in years rather than minutes. But the density of reference points is sufficient to provide orientation. In intergalactic space, the reference frame is defined by the two galaxies being left and approached, with nothing of navigational significance between them. Over a journey lasting millions of years, stellar drift within both galaxies will change their appearances substantially. The positions of individual stars used as reference points will shift, and the accumulated uncertainties in trajectory calculation will grow without the feedback that near real-time communication provides. At a transit speed of 10% of the speed of light, a positional error of 1 part in 10 million in the initial trajectory translates to a missed distance of roughly 250,000 light-years at Andromeda, comparable to the diameter of the Milky Way itself. The spacecraft would pass through intergalactic space and arrive in the general neighbourhood of Andromeda, but potentially far from its centre or from any particular target within it. Mid-course corrections are possible in principle, but require knowing the spacecraft's actual position during transit, which in the absence of nearby reference points and with communication delays of millions of years, can only be determined by measuring the apparent positions of the two galaxies relative to background objects, a process that requires months of observation to achieve meaningful precision at any single point in the journey. The entire navigational architecture of intergalactic travel is a solved problem in principle, but an unsolved problem in practice, requiring systems and capabilities that do not exist, and that would themselves require enormous investment to develop. Other galaxies beyond Andromeda and how far they really are. Andromeda is the nearest large galaxy to the Milky Way, but it is not the nearest galaxy in an absolute sense. Several dwarf galaxies orbit the Milky Way at distances of tens to hundreds of thousands of light-years, all well within the distance to Andromeda. The Large Magellanic Cloud is roughly 160,000 light-years away. The Small Magellanic Cloud is approximately 200,000 light-years distant. The Sagittarius Dwarf Spheroidal Galaxy, discovered only in 1994, is being actively disrupted by the Milky Way's tidal forces and currently passes through the galactic disk at a distance of roughly 70,000 light-years from the galactic centre. The Canis Major Dwarf, if it is a true dwarf galaxy rather than a tidal stream artifact, sits approximately 25,000 light-years from the galactic centre, closer than the Sun itself. These nearby dwarfs are interesting but do not change the fundamental analysis. They are within the Milky Way's gravitational dominion, in various stages of being absorbed, and reaching them would still require crossing tens to hundreds of thousands of light-years, with no technology currently capable of doing so in under thousands of years. They are closer than Andromeda in the way that the suburbs are closer than the next city over, still unreachable by walking. Beyond the local group, the distances escalate rapidly, and the character of the problem changes from merely astronomical to cosmological. The Triangulum Galaxy M33, the third largest member of the local group, is 2.73 million light-years away, slightly farther than Andromeda. The IC10 Irregular Galaxy, an active starburst system in the local group, is approximately 2.2 million light-years distant. The NGC 6822 Dwarf Irregular is roughly 1.6 million light-years away. All of these are within the local group and are gravitationally associated with the Milky Way Andromeda system. The nearest galaxy group beyond the local group is the Sculptor group, a loose association of galaxies centered approximately 11 to 14 million light-years from Earth. The nearest member of the Sculptor group, NGC 300, is approximately 6.1 million light-years away. At this distance, the light travel time is 6 million years. The hominid lineage 6 million years ago had barely diverged from the common ancestor of humans and chimpanzees. Lucy, the famous Australopithecus afarensis specimen, would not exist for another 2 million years. The light arriving from NGC 300 tonight left that galaxy when the last common ancestor of humans and modern great apes was walking the forests of Africa. The Centaurus A group, another nearby galaxy group, contains the giant elliptical galaxy NGC 5128, known as Centaurus A, at approximately 11 to 12 million light-years distance. Centaurus A is one of the most studied radio galaxies in the sky, harbouring a supermassive black hole of approximately 55 million solar masses that powers a pair of enormous relativistic jets extending hundreds of thousands of light-years from the galaxy's centre. The jets are producing a continuous output of energetic particles and electromagnetic radiation that makes Centaurus A one of the most luminous sources in the sky at radio wavelengths. Despite its prominence and its relatively small distance by extragalactic standards, no human artifact has travelled more than a tiny fraction of a light-year from Earth, let alone the 11 million light-years separating us from Centaurus A. The Virgo cluster, at approximately 53 million light-years, is the nearest large galaxy cluster, a gravitationally bound collection of roughly 1,300 galaxies, dominated by giant ellipticals, including M87, whose supermassive black hole of approximately 6.5 billion solar masses was the first black hole to be directly imaged by the Event Horizon Telescope collaboration in April 2019. The image required coordinating radio telescopes across the entire surface of the Earth into a single virtual telescope the size of the planet, achieving the resolution necessary to image the shadow of a black hole 53 million light-years away. The light in that image left M87 53 million years ago, during the Eocene epoch on Earth, when the continents were in roughly recognizable but distinctly different positions. The climate was warm enough for forests to grow near the poles, and the mammals diversifying after the extinction of non-avian dinosaurs had not yet produced the horse, the whale, or any primate larger than a cat. The Coma cluster, at approximately 320 million light-years, is among the richest and most studied galaxy clusters in the sky, containing more than 1,000 galaxies within a volume roughly 20 million light-years across. The Coma cluster was the site of Fritz Zwicky's 1933 discovery that galaxy clusters contain far more mass than is visible in their stars, the first observational evidence for dark matter, which he called Dunkel Materie, dark matter, in the paper. The light arriving from the Coma cluster tonight left those galaxies 320 million years ago, during the Carboniferous period on Earth, when the land was covered by dense coal forests, when insects grew to enormous sizes in the oxygen-rich atmosphere, and when the ancestors of all terrestrial vertebrates were still amphibians that had not yet developed the amniotic egg that would allow fully terrestrial reproduction. The Perseus cluster, approximately 240 million light-years distant, is a galaxy cluster notable for containing one of the most massive black holes known in the galaxy NGC 1277, estimated at approximately 17 billion solar masses, which would make it one of the largest black holes in the local universe. In 2003, Andrew Fabian at the Cambridge Institute of Astronomy detected sound waves propagating through the hot X-ray emitting gas that fills the Perseus cluster, produced by the periodic outbursts of the central active galactic nucleus in the dominant cluster galaxy NGC 1275. The sound waves correspond to a note approximately B-flat, 57 octaves below middle C, with a period of roughly 10 million years far below the range of human hearing. They are nonetheless real acoustic waves propagating through a physical medium, and they reveal that the central black hole has been regularly injecting enormous energy into the cluster gas at intervals of millions of years. The Shapley supercluster, at approximately 650 million light-years, is the largest concentration of galaxies within the nearby universe, a vast overdensity containing dozens of galaxy clusters and thousands of individual galaxies spread across a region roughly 300 million light-years across. The peculiar velocities of galaxies throughout the local universe, including the Milky Way and the local group, show components pointing toward the Shapley supercluster, indicating that this enormous concentration of mass is gravitationally influencing the motions of matter across hundreds of millions of light-years. The Milky Way is being pulled toward the Shapley supercluster at several hundred kilometers per second, a motion that will continue for billions of years but will never result in arrival. The expansion of space will prevent any approach to the Shapley supercluster within any cosmologically relevant time frame. Each of these objects, the Virgo cluster, the Coma cluster, the Perseus cluster, the Shapley supercluster, represents a frontier of known structure that is simultaneously accessible to observation and permanently inaccessible to any physical contact from Earth. We know the Perseus cluster contains sound waves generated by a black hole. We know the Shapley supercluster is pulling on the Milky Way. We can observe, classify, and understand these phenomena in detail from Earth. And we can do nothing about any of them, influence none of them, send nothing to them, and receive nothing from them except the photons that happen to be traveling in our direction at the speed of light, carrying information about a past that predates human existence by tens to hundreds of millions of years. The accumulation of knowledge about unreachable objects is one of the defining features of astronomy, and it is most stark when the objects are galaxies and galaxy clusters at distances that translate the light travel time into geological and evolutionary epochs. The Fermi paradox and what the distance implies, the distance to Andromeda and to all galaxies beyond the local group, is relevant not only for the question of whether humanity can reach them, but for the question of whether any intelligence anywhere can bridge intergalactic distances. The Fermi paradox, the observation that the universe appears old enough and large enough to have produced technological civilizations far in advance of humanity, yet no evidence of such civilizations has been detected, acquires a specific additional dimension when the physical constraints of intergalactic distance are applied. The universe is approximately 13.8 billion years old. The Milky Way began forming approximately 13.5 billion years ago. The first generation of stars formed within a few hundred million years of the Big Bang. Subsequent generations of stars, enriched with the heavy elements produced in earlier stellar generations, formed over the following billions of years. Planetary systems capable of supporting chemistry complex enough for life have been forming for at least 8 to 10 billion years. A civilization that arose around a star 10 billion years ago would have had 10 billion years to develop technology, expand across its galaxy, and potentially reach neighboring galaxies. 10 billion years of technological development is an incomprehensible head start relative to the 3 or 4 billion years of life on Earth and the roughly 10,000 years of human technological civilization. If any civilization in the observable universe has followed a trajectory even remotely resembling the exponential growth in technological capability that human civilization has demonstrated over the past 2 centuries, it should have reached capabilities that make the engineering challenges of interstellar and even intergalactic travel tractable, however difficult they appear from our current perspective. Yet no evidence of such civilizations has been found, in the form of signals, artifacts, megastructures, or any other detectable signature. The distance to Andromeda provides one possible contribution to the resolution of this silence. Even a civilization 10 billion years old, with technology beyond our ability to imagine, faces the same fundamental physical constraints imposed by the speed of light and the energy required for relativistic travel. If crossing 2.537 million light-years requires energy inputs comparable to the total output of a star over millions of years, then the resource requirements for intergalactic colonization are simply staggering, even for a K3 civilization on the Kardashev scale. one that has mastered the energy output of an entire galaxy. A K2 civilization, controlling the full energy output of its star, would still face a travel time to Andromeda of millions of years even at relativistic speeds, and a K3 civilization harnessing galactic energy could cross the distance faster, but would still require crossing 2.537 million light-years at the speed of light as an absolute lower bound. The local group constraint is relevant here. Any civilization confined by the same physics to its local group of galaxies faces a bounded, accessible universe. The gravitationally bound cluster of galaxies it inhabits is accessible in principle over timescales measured in millions to billions of years. Everything beyond is progressively, irreversibly receding. A civilization that developed in an isolated galaxy group, far from any other group, would be as cosmologically isolated as a local group civilization, separated from all neighboring groups by distances comparable to those separating the local group from the Sculptor group or the Centaurus A group. The silence of the universe may therefore reflect not the absence of technological civilizations, but the physical reality that each such civilization is confined to its own local group equivalent, unable to cross the intergalactic void on any timescale that makes contact meaningful. Two civilizations in neighboring galaxy groups, separated by 10 to 20 million light-years, cannot communicate with a round-trip signal time shorter than 20 to 40 million years, cannot visit each other without journeys lasting millions of years, and cannot affect each other in any way that would be detectable within the lifespan of a single civilization. They are isolated not by choice or by silence, but by physics. The silence of the universe may therefore reflect not the absence of technological civilizations, but the physical reality that each such civilization is confined to its own local group equivalent, unable to cross the intergalactic void on any timescale that makes contact meaningful. Two civilizations in neighboring galaxy groups separated by 10 to 20 million light-years cannot communicate with a round-trip signal time shorter than 20 to 40 million years, cannot visit each other without journeys lasting millions of years, and cannot affect each other in any way that would be detectable within the lifespan of a single civilization. They are isolated not by choice or by silence, but by physics. This does not resolve the Fermi paradox in the sense of identifying a single definitive explanation for the absence of detected signals from nearby civilizations within the Milky Way. But it does add a layer to the understanding of cosmic isolation. Even if the galaxy is full of civilizations, each galaxy is cosmologically alone, separated from its nearest large galactic neighbor by millions of light-years, and from all significant galaxy groups beyond by tens to hundreds of millions of light-years. The universe contains an enormous number of galaxies, but they are organized into isolated clusters separated by voids so large that crossing them is, for any physically realistic civilization, functionally impossible on any timescale shorter than the age of the universe itself. There is a specific quantitative way to appreciate the scale of the Fermi paradox's intergalactic dimension. If a civilization launched spacecraft from its home galaxy toward every neighboring galaxy in its local group equivalent at 10% of the speed of light, filling its local group with inhabited worlds over a period of tens of millions of years, it would still be confined to its local group. The nearest neighboring galaxy group would be separated by 10 to 20 million light-years of intergalactic void that, at 10% of light speed, requires 100 to 200 million years to cross. During that transit time, the civilization's home galaxy group would have undergone enormous internal changes. Stellar populations would have evolved substantially, and the technological civilization driving the expansion might itself have transformed beyond recognition or cease to exist. The wave of expansion would slow and stop not at any physical barrier, but at the edge of what any continuous civilizational project can sustain over the necessary timescales. This is what makes the local group the natural unit of civilizational geography. if civilizational geography is a meaningful concept. Within the local group, travel between galaxies requires millions of years, but is not permanently prohibited by the expansion of space. Between local groups, the expansion of space is actively working against any transit attempt, adding distance continuously and ensuring that even the nearest neighbouring group becomes progressively harder to reach over cosmological time. If dark energy continues to accelerate the expansion at its current rate, the nearest neighbouring galaxy groups will eventually become permanently inaccessible, not merely difficult. The window for intergalactic travel between local group equivalents, if any such window exists at all given the energy requirements, is finite and closing. Each year of delay in attempting such travel corresponds to a slightly longer and more energy-intensive journey, because the target is continuously farther away. The evolving picture of the Andromeda Galaxy. The past decade has produced a transformation in our knowledge of the Andromeda Galaxy, driven by the combination of deep photometric surveys, improved spectroscopic capabilities, and the deployment of the James Webb Space Telescope. The galaxy that was known in broad strokes in 2014 is now understood in considerably finer detail, and several of the new findings have challenged or refined long-standing models of galaxy formation and evolution. The PANDAS survey, completed in the early 2010s using the Canada-France-Hawaii telescope, mapped the extended stellar halo of Andromeda across a region more than 150 kiloparsecs in radius from the galaxy's centre, covering an area of the sky several hundred times larger than the full moon. The survey revealed an extraordinary richness of substructure in the halo, at least 17 distinct stellar streams, several new dwarf galaxy companions, shells and clouds of stars that are the remnants of ancient merger events, and a complex pattern of overdensities and underdensities that encode the entire history of mass assembly over billions of years. The giant stellar stream, the most prominent tidal feature in Andromeda's halo, was traced in detail by the survey and found to extend further and contain more mass than previously estimated. The progenitor of the stream, the galaxy that was disrupted to produce it, was likely a galaxy comparable to the Small Magellanic Cloud in mass, perhaps containing a few 100 million stars that fell into Andromeda's gravitational field roughly 1 to 2 billion years ago, and was torn apart over multiple orbits. The stars from this disrupted galaxy now form an arc roughly 200,000 light-years long, the ghostly remnant of an absorbed companion. The panchromatic Hubble Andromeda Treasury Survey, completed using the Hubble Space Telescope over several years, ending in the mid-2010s, resolved more than 117 million individual stars in the disk of Andromeda across 828 pointings of Hubble's Wide Field Camera 3. The survey produced colour magnitude diagrams, plots of stellar brightness against stellar colour for the full resolved stellar population of the galaxy's disk, from which the star formation history of different regions of the disk was reconstructed. The analysis showed that Andromeda's star formation history differs significantly from the Milky Way's. While the Milky Way appears to have formed the bulk of its stellar mass early and then continued forming stars at a roughly steady rate, Andromeda shows evidence of a more dramatic star formation history, with significant episodes of enhanced star formation at various epochs, likely triggered by merger events with other galaxies. The James Webb Space Telescope, operating from 2022 onward, has extended the reach of resolved stellar population studies in Andromeda into the infrared, allowing the detection and characterization of cool, low-luminosity stars that were invisible to Hubble at optical wavelengths. Red giant branch stars, which reach a characteristic maximum luminosity determined by helium flash in their cores, serve as a standard candle that provides an independent distance measurement to Andromeda. Webb's infrared photometry has produced refined measurements of the red giant branch tip in multiple regions of Andromeda, contributing to the ongoing effort to precisely calibrate the extragalactic distance scale and address the Hubble tension, the discrepancy between different methods of measuring the universe's expansion rate. One of the most intriguing recent developments in Andromeda research concerns the galaxy's halo gas. Deep ultraviolet spectroscopy, using the Hubble Space Telescope's cosmic origin spectrograph, observing background quasars whose light passes through Andromeda's extended gaseous halo before reaching Earth, has revealed the presence of warm gas extending to at least 300 kiloparsecs from Andromeda's center, comparable to or exceeding the estimated distance between the Milky Way and Andromeda's own halo boundary. The Milky Way has a similar extended gaseous halo. This means the halos of the two galaxies are likely already interacting, their outermost gaseous envelopes touching or overlapping across the intergalactic space separating them, even though the stellar disks are still 2.537 million light-years apart. In a physical sense, the collision of the Milky Way and Andromeda has already begun at the level of their diffuse gaseous atmospheres. The stellar disks are separated by 2.537 million light-years. The halos interpenetrate already. The hypothetical of sending a signal, not a spacecraft. The impossibility of sending any physical object to Andromeda on any human timescale raises a natural question. What about sending a signal? Radio waves, light, and other forms of electromagnetic radiation travel at the speed of light, the fastest anything can move through space. They require no propulsion, no fuel, no structural integrity over millions of years. Could humanity communicate with any hypothetical intelligence in Andromeda, even if it can never travel there? The signal travel time is 2.537 million years each way. A message sent from Earth today would arrive at Andromeda in the year 2,539,025 CE, approximately. A reply, if any intelligence in Andromeda sent one immediately upon reception, would arrive on Earth in the year 5,076,050 CE. The round-trip communication time exceeds 5 million years. No institution, no civilization, no species has maintained recognizable continuity for 5 million years. Homo sapiens has existed for approximately 300,000 years. Our earliest identifiable ancestors in the hominid lineage diverged from the common ancestor of humans and chimpanzees, roughly 5 to 7 million years ago. Those proto-hominids bore no meaningful resemblance in cognition, technology, or culture to modern humans. Whatever entity on Earth received a reply from Andromeda in 5 million years would be as unrecognizable relative to us as we are relative to Australopithecus. The signal itself presents its own challenges. Broadcasting a radio signal powerful enough to be detectable at Andromeda's distance requires extraordinary transmitter power. The relationship between transmitted power, antenna gain, distance, and received power is described by the Friis transmission equation. For a signal detectable by an antenna comparable to the Arecibo Observatory, which with a diameter of 305 meters was the largest single-dish radio telescope ever built before its collapse in 2020. At Andromeda's distance, the required transmitter power scales as the square of the distance divided by the product of the transmitting and receiving antenna areas and the wavelength squared. At 2.537 million light-years, compared to the distance to a star 100 light-years away, the required power increases by the square of the distance ratio, approximately 600 million times. Broadcasting a signal detectable by a civilization in Andromeda using a modest radio telescope would require a transmitter radiating as much power as a significant fraction of the Sun's total luminosity, directed entirely at Andromeda. No technology currently available or foreseeable on any near-term horizon approaches this capability. The most powerful radar transmitters ever built on Earth, designed for planetary radar astronomy, produce outputs of order 1 megawatt. The Sun's luminosity is approximately 3.8 times 10 to the 26th watts. The required transmitter power for intergalactic signaling exceeds all of human industrial capacity by a margin so large that it places such communication firmly in the category of K2, or K3 civilization capability on the Kardashev scale, meaning it requires either the full harnessing of a star's energy output or the harnessing of a galaxy's energy output. Laser communication using coherent narrow-beam optical signals is more energy efficient than radio for large distances because the beam divergence is much smaller, concentrating more power into the receiving aperture. But even with laser communication, the fundamental photon budget at intergalactic distances requires power inputs that dwarf current human energy production. The photon flux from even the most powerful lasers built by humanity falls off as the inverse square of distance, and at 2.537 million light-years, the number of photons per unit time arriving at a receiver of any physically plausible aperture is effectively zero for any transmitter power achievable with current or near-future technology. The only realistic scenario for intergalactic communication from Earth to Andromeda, setting aside entirely the question of whether anything in Andromeda is listening, would involve a civilization operating at K2 scale or above, dedicated entirely to the transmission problem, transmitting for millions of years to ensure a sustained signal rather than a brief pulse. No such civilization currently exists on Earth, and the civilization that would receive any reply 5 million years after transmission bears no predictable relationship to the one that sent the message. The question of whether anything in Andromeda might be listening connects directly to the question of whether life and intelligence are common in the universe. Andromeda contains approximately 1 trillion stars. Many of those stars are solar type, burning stably on the main sequence for billions of years, capable of maintaining habitable planetary environments for the timescales that complex life and intelligence require. Even if the probability of life arising around any individual star is extraordinarily small, 1 trillion opportunities provides a large statistical sample. If the probability of technological civilization arising around any given star system over 10 billion years is 1 in a billion, Andromeda would contain roughly 1,000 technological civilizations at any given time. If it is 1 in a trillion, Andromeda would contain, on average, 1 such civilization. Whether any of these hypothetical civilizations could detect signals from the Milky Way depends on the same power and sensitivity calculations that constrain our own transmission capabilities. A civilization in Andromeda with technology comparable to our own could no more detect Earth's radio broadcasts than Earth could detect comparable broadcasts from Andromeda. Mutual detectability requires either that both civilizations operate at K2 scale or above, with transmitters comparable in power to stars, or that the civilizations are close enough in their respective galaxies that signals can cross the intervening distance with sufficient intensity to be detectable by plausible receivers. Within a single galaxy, the interstellar distances are small enough that a K1 civilization with technology modestly beyond our own could potentially broadcast detectable signals to a large fraction of the galaxy. Between galaxies, even K2 civilizations face the inverse square law applied to 2.537 million light-years and the required transmitter power scales accordingly. The search for extraterrestrial intelligence programs that have been operating since Frank Drake's pioneering project OSMA in 1960 at the National Radio Astronomy Observatory in Greenbank, West Virginia, have been searching primarily within the Milky Way, scanning nearby stars for signals at radio frequencies and, more recently, at optical wavelengths. The Breakthrough Listen initiative, funded by Yuri Milner, beginning in 2016 and conducted at the Greenbank Telescope in West Virginia and the Parkes Observatory in Australia, has surveyed thousands of nearby stars and several nearby galaxies, including Andromeda at radio and optical wavelengths with unprecedented sensitivity. No confirmed signals of extraterrestrial technological origin have been detected. Whether this absence reflects the rarity of technological civilizations, the challenges of interstellar, let alone intergalactic communication, or simply the limitations of our current search coverage is not determinable from the data. The view from Andromeda looking back at us. Perspective is one of the most useful tools in understanding distances that resist direct intuition. What does the Milky Way look like from Andromeda? What does Earth look like? What would any hypothetical observer in Andromeda see if they looked toward our galaxy tonight? From Andromeda, the Milky Way appears as a spiral galaxy roughly 2.537 million light-years away. At that distance, with the angular resolution of instruments comparable to the Hubble Space Telescope, the Milky Way would be resolved into individual bright star clusters and nebulae, its spiral arm structure traced by the blue light of young massive stars and the reddish glow of ionized hydrogen gas. The general morphology of the Milky Way's disk would be visible, though the precise structure of the spiral arms would be uncertain due to our own galaxy's irregular and somewhat ambiguous arm configuration. The central bulge would appear as a bright, concentrated nucleus. The Milky Way's satellite galaxies, including the Magellanic Clouds, would be visible as small companions orbiting the larger spiral. What would not be visible from Andromeda is Earth, the Sun, or any individual star in the Milky Way with any current technology, and the images arriving at Andromeda tonight show the Milky Way as it was 2.537 million years ago. The Sun, an unremarkable G-type main sequence star in the outer third of the Milky Way's disk, contributes its photons to the collective luminosity of the galaxy, but is indistinguishable as an individual source from any other comparable star at intergalactic distances. Earth, orbiting the Sun at a distance of 1 astronomical unit and reflecting a tiny fraction of the Sun's light, is completely invisible at any distance beyond a few thousand light-years, even with the most sensitive instruments humanity has built. From Andromeda, Earth does not exist as a detectable object by any means available to a civilization with technology comparable to our own. The light leaving Earth tonight that is heading toward Andromeda will arrive there in 2.537 million years. By that time, the Sun will have consumed an additional 2.537 million years of hydrogen fuel, having aged by approximately 0.025% of its total main sequence lifespan. The Earth's orbital parameters will have changed slightly due to the gradual mass loss of the Sun. The continents will have moved by tens to hundreds of kilometers relative to each other as plate tectonics continues. Whatever biological organisms, if any, inhabit Earth at that time will bear no predictable relationship to Homo sapiens or to any currently existing species. The total electromagnetic output of Earth, the aggregate of all radio transmissions, reflected sunlight, and thermal emission that constitutes humanity's electromagnetic signature, will have been travelling for 2.537 million years, and will arrive at Andromeda as an extraordinarily faint smear of radiation, utterly indistinguishable from the natural emission of the Milky Way at any wavelength, carrying no discernible information about the civilization that produced it. We are invisible to Andromeda. We will remain invisible to Andromeda for any foreseeable future. The light from the first human campfires, lit perhaps 400,000 years ago, has travelled 400,000 light-years toward Andromeda and is still 2.137 million light-years from its destination. The radio broadcasts that began in the early 20th century have travelled roughly 120 light-years, a distance that encompasses a few hundred nearby stellar systems and is less than 0.005% of the distance to Andromeda. The nearest extraterrestrial civilization that could have detected those earliest radio broadcasts and sent a reply already received is within 60 light-years. Andromeda is 42,000 times farther than that. The invisibility is mutual and complete in every band of the electromagnetic spectrum at the power levels of any human technology. It is broken only by the aggregate emission of an entire galaxy. The Milky Way as a whole is detectable from Andromeda, not because any individual object in the Milky Way is bright enough to be seen, but because 1 trillion stars combined produce a total luminosity equivalent to roughly 10 billion suns, which is sufficient to constitute a visible, resolvable object at 2.537 million light-years. Any civilization in Andromeda with astronomy comparable to ours would see the Milky Way as we see Andromeda, a spiral galaxy, a fuzzy patch of light resolvable into stars with sufficient telescope aperture, its total luminosity measurable, its recession velocity 0 or slightly negative, indicating a bound companion, but its individual stars distinguishable only with the equivalent of our Hubble Space Telescope pointed at it for extended exposures. And even with such observations, no individual star in the Milky Way is uniquely identifiable from Andromeda as interesting or inhabited, or worth pointing a more powerful instrument at. The Sun is one of 200 billion comparable stars in the galaxy's disk, producing no anomalous emission at any wavelength that would attract astronomical attention. The only conceivable way Earth could become visible to Andromeda on any timescale relevant to the current state of human civilization is if some event of stellar or superstellar magnitude occurred in or near the solar system, such as the Sun becoming an active gamma-ray burst source, or if human civilization deliberately constructed a transmitter of stellar power output specifically directed toward Andromeda. Neither scenario is plausible within any foreseeable future. Earth will remain, from Andromeda's perspective, an invisible speck embedded in an unremarkable star's unremarkable planetary system in an unremarkable region of an ordinary spiral galaxy, for as long as Earth and Andromeda both exist as distinct objects. The merger of the two galaxies in 5 billion years will not change this fundamental anonymity. After the merger, the Sun and whatever planets orbit it at that time will be one of 2 trillion stars in the merged Milky system, no more distinguishable from the billions of former Andromedan stars around it than before. The collision that will reshape the night sky. The distance to Andromeda and to all galaxies is not merely a current fact. It is a dynamic quantity whose evolution over the future history of the universe determines the ultimate fate of all matter, energy, and information in the cosmos. Understanding the trajectory of cosmic distances into the far future is understanding the context within which any long-term project of civilization, exploration, or knowledge building must operate. On the timescale of 5 billion years, the Sun will exhaust its core hydrogen and expand into a red giant, engulfing Mercury, Venus, and possibly Earth. The Milky Way and Andromeda will be well into their merger process, with the first close approach occurring approximately 4.5 billion years from now. The combined system will be assembling into Milkomeda, the merged elliptical galaxy that will be the product of billions of years of gravitational interaction. The current 2.537 million light-year separation between the two galaxies will have closed entirely, replaced by a new gravitational equilibrium in which the stars of both galaxies orbit the combined center of mass. On the timescale of 100 billion years, the expansion of the universe driven by dark energy will have carried all galaxies beyond the local group across the cosmic event horizon. The night sky over Earth, if any civilization exists to observe it, will show only the stars of Milkomeda and its remaining satellite companions. Every other galaxy in the observable universe will have receded beyond the horizon, its light redshifted to wavelengths too long to detect, its existence inferable only from the cosmological models of whatever physics understanding survives to that era. The universe will appear to consist of a single, large stellar system adrift in an otherwise empty and featureless space. On the timescale of 10 trillion years, the last stars of Milkomeda will be exhausting their fuel. The most massive stars will long since have exploded as supernovae and left behind neutron stars and black holes. Medium-mass stars like the Sun will have become white dwarfs, cooling slowly toward absolute zero over timescales of quadrillions of years. The lowest mass red dwarf stars, burning their hydrogen fuel so slowly that they shine for trillions of years, will still be providing warmth and light to any planetary systems that remain in stable orbits. These red dwarfs are the last generation of stars, the terminal phase of the Milky Way, and Andromeda's stellar populations before the universe enters its long dark age. Lawrence Krauss and Robert Scherer, writing in the Journal of Relativity and Gravitation in 2008, analysed the implications of an accelerating universe for the long-term availability of cosmological knowledge. Their conclusion, referenced also in an earlier discussion in Part 1 of this script, is that in approximately 100 billion years, any civilization that comes into existence will lack the observational evidence to reconstruct the history of the universe. The cosmic microwave background will have been redshifted to wavelengths far too long to detect with any physical instrument. The recession of all external galaxies will be unobservable. The expansion of the universe will be unmeasurable because there are no distance indicators available. Such a civilization would be unable to discover that the universe ever had a Big Bang, that it ever was hot and dense, or that it ever contained the vast array of galaxies that fill our current night sky. They would conclude, rationally, that they inhabited the only galaxy in existence, surrounded by infinite static empty space. Beyond 10 trillion years, the last red dwarf stars gradually exhaust their hydrogen and transition to cooling white dwarfs. The merged Milky system, no longer producing new stars in significant numbers due to the exhaustion of its gas reservoirs, becomes a system of cooling stellar remnants. White dwarfs, neutron stars, and black holes orbiting a common centre of mass, increasingly dark and cold. Black holes, the most extreme stellar remnants, are not permanent. Stephen Hawking's 1974 theoretical work showed that black holes should slowly radiate energy through a quantum process at their event horizons, gradually losing mass and eventually evaporating entirely. A stellar mass black hole of a few solar masses evaporates on a timescale of approximately 10 to the 67th years. The supermassive black holes formed in galaxy mergers with masses of billions of solar masses evaporate on timescales of approximately 10 to the 99th years. After the last black hole evaporates, the universe contains only the sparse radiation left over from all these processes: photons, neutrinos, and whatever remains of matter after proton decay, if protons are in fact unstable, drifting through an expanding space that grows darker and colder without limit. The distance to Andromeda is a single number in this vast temporal landscape: 2.537 million light-years, meaningful for roughly 5 billion years, until the merger eliminates it, existing against a background of cosmic timescales that dwarf it by factors of millions and billions. The specific fact of Andromeda's distance encodes the state of the local group at this particular moment in the universe's history, a moment that is, from the universe's perspective, very early. We are currently only 13.8 billion years into a future that extends for at least tens of trillions of years and possibly longer. We are not seeing the universe in its final state or even its middle age. We are in its youth, at an epoch when distances between galaxies are still moderate, when the cosmic microwave background is still detectable, when the expansion of the universe is measurable, and when the Andromeda Galaxy is close enough to resolve into individual stars from Earth's surface on a clear night. We live in a period of maximum cosmological legibility. The evidence for the Big Bang is still visible in the cosmic microwave background. The recession of distant galaxies is measurable from thousands of redshift surveys. The large-scale structure of the universe, the cosmic web of filaments and voids that traces the distribution of matter, is accessible to observation. The distance to Andromeda can be measured by multiple independent methods. None of this will remain accessible forever. We happen to exist at the only epoch in the universe's history, a window of perhaps 100 billion years out of a total lifespan measured in trillions, during which the full picture is available to be read. The distance to Andromeda is part of that picture. It is a specific number, 2.537 million light-years, that will change over the next 5 billion years as Andromeda approaches and eventually merges with the Milky Way. After the merger, the concept of the distance to Andromeda will become meaningless. The two galaxies will be one. The specific measurement that currently defines the boundary between our galaxy and the next, between the familiar and the unreachable, will no longer exist. What will remain is Andromeda, a merged elliptical galaxy, slowly depleting its stellar fuel over trillions of years, surrounded by the receding darkness of an expanding universe from which all other galaxies have long since vanished. The cosmic future taking shape before us. After working through the physics of the distance to Andromeda, through the impossibility of physical travel, the inaccessibility of meaningful communication, the accelerating expansion that is shrinking the universe's accessible domain, and the eventual merger that will eliminate the distance entirely in 5 billion years, the question remains, what is the distance to Andromeda actually telling us? It is telling us something about the scale of isolation that is built into the structure of the universe. The universe contains approximately 2 trillion galaxies. They are organized into groups and clusters, each group gravitationally bound internally, but separated from neighboring groups by distances of 10 to 20 million light-years that are, for any realistic physical civilization, uncrossable on any timescale shorter than the age of the universe. Each gravitationally bound group is an island. The local group is our island. Andromeda is the nearest large neighbor on our island. Everything else is either in our group or permanently out of reach on any cosmological timescale relevant to life, civilization, or any physical process that can be meaningfully connected to a specific place of origin. This is not a limitation that future technology is likely to overcome. The speed of light is not a technology barrier in the sense that chemical rockets were a technology barrier to reaching the moon. It is a property of space-time, a consequence of special relativity that has been confirmed to extraordinary precision by a century of experimental physics. The expansion of the universe is not a barrier that future engineering can reverse. It is a consequence of general relativity and the energy content of the universe, confirmed by a century of observational cosmology. The energy required for relativistic travel is not merely large in the way that building a particle accelerator is large. It is large in the way that rearranging the mass energy of stellar systems is large. These are not gaps in human capability waiting to be closed. They are features of the universe. What the distance to Andromeda is telling us in its most direct form is that the universe is not built for traversal by its inhabitants. It is not organized on human scales or civilizational scales or even biological scales. It is organized on cosmic scales, millions of light years between galaxies, billions of light years across the observable universe, billions of years of age, trillions of years of future lifespan for the last stars. Every scale that matters to the universe is orders of magnitude beyond the scale that matters to any life form that has ever existed on Earth. This does not mean the universe is indifferent to life in any morally relevant sense. The universe has no preferences. It does not care whether anything lives or dies, whether civilizations rise or fall, whether the distance to Andromeda is crossed or not. It operates by its physical laws without reference to the desires of the matter it contains. The distance to Andromeda is 2.537 million light-years because that is where Andromeda is, and where it is follows from the initial conditions of the universe and the subsequent action of gravity and expansion over 13.8 billion years. The difficulty of crossing that distance is a consequence of the physics that governs all matter and energy. Neither fact contains any message about humanity's importance or lack thereof. What it does contain is a context. We exist on a planet orbiting an ordinary star in an ordinary galaxy. Our galaxy is one of 2 dominant members of a small gravitationally bound cluster containing roughly 80 galaxies spread across 10 million light-years. That cluster is one of the smaller concentrations of matter in a universe containing 2 trillion galaxies. We are nowhere in particular, and everywhere in particular is the same kind of nowhere. The Milky Way and Andromeda are the 2 most significant galaxies in our local group, but from the perspective of any other galaxy group, they are 2 of 80 unremarkable members of a minor cluster at the edge of the Laniakea supercluster. And Laniakea itself is one supercluster among thousands in the observable universe, not particularly large, not particularly rich, not distinguished by any property that would draw the attention of a cosmologist surveying the large-scale structure of the universe. The distance to Andromeda is worse than you thought, because the numbers involved are not merely large. They are large in a way that removes the concept of reaching or touching or affecting from the domain of any physical process that originates on Earth. You can see Andromeda on a dark night. You can photograph it in extraordinary detail. You can reconstruct the history of its stellar populations across billions of years. You can calculate the trajectory of its merger with the Milky Way over the next 5 billion years. You can know it in the full scientific sense of the word, from a distance of 2.537 million light-years. What you cannot do is go there or send anything there or receive anything from there within any time frame that connects meaningfully to human life or civilization as it currently exists or can be plausibly imagined to exist. That asymmetry between the richness of what can be known from afar and the absolute impossibility of physical contact is the defining feature of humanity's relationship with the universe beyond the local group. We are observers. We are not travelers. The universe allows us to watch from the inside, to accumulate knowledge about distances and timescales and physical processes that dwarf us in every measurable way, while simultaneously ensuring that we can never touch most of what we observe. The distance to the next galaxy is not a challenge waiting to be overcome. It is a fundamental feature of the universe we happen to inhabit, built into its physics from the first moments of its existence, and it will remain exactly as impassable on the day the last star in the Milky Way burns out as it is tonight, when you look up and see Andromeda as a faint smudge in Orion's neighborhood, carrying light that left it before your species existed, arriving at your eye at the only speed anything in the universe is allowed to move: the Great Barrier between the stars. The Andromeda Galaxy is the most studied, unreachable object in existence. We have resolved its individual stars. We have mapped its stellar streams and satellite companions. We have traced its merger history across billions of years and calculated its collision course with our own galaxy across the next 5 billion. We have done all of this using nothing but photons, particles of light that cross 2.537 million light-years to reach our instruments, carrying information about a place no physical object launched from Earth will ever visit within any time frame that bears a meaningful relationship to human civilization. The knowledge is real and extraordinary. The distance is worse than any number conveys. What makes it worse is not the number itself. It is the physics behind the number, the speed of light as an absolute limit, the energy requirements of relativistic travel as a practical impossibility, the expansion of space actively increasing the distances to everything beyond the local group, and the accelerating universe systematically removing galaxies from the domain of the accessible at a rate that will, in 100 billion years, leave our descendants in a universe that appears to contain only a single galaxy. We exist in the one window of cosmic time when the full extent of the universe is legible. We are reading it from a fixed position, unable to move towards what we observe, watching it recede. The distance to the next galaxy is not a problem to be solved. It is a physical reality of the universe that built us, contained in the structure of space-time itself from the first moments of the Big Bang. Andromeda will merge with the Milky Way in 5 billion years, eliminating the distance between them by eliminating the distinction between them. Until then, it sits exactly 2.537 million light-years away, visible, knowable, unreachable, carrying light from a time before humanity existed toward eyes that will see it for exactly as long as humanity lasts, which is a fraction of the time the light has been traveling.